Welcome to the 18th class meeting of the Introduction to DSP. As always, there will be a homework, and this time MATLAB again. So you will enjoy some signal processing problems. Unfortunately, we are going to have quiz 2 coming soon. It's on May 1st during the 22nd class meeting. And similar to the previous quiz and midterm exam, it will be a close everything quiz, but you need to bring your digital device to see the, at least upload your answer to the PLMS. Got it? So here goes the overview. Today, we are really finishing chapter 4 and jump to chapter 8. That's what I hope. So we start to study the core of the undergraduate DSP course, the discrete Fourier transform. So we have a lot of expectations. Here was the review, and I took a lot of time today to prepare for the review because I decided to talk about this multistage decimation analysis, multistage interpolation analysis. That's what I prepared. So let me talk about it first. And also, in the last class meeting, I just mentioned simply there are some important topics related to two-channel or multi-channel filter banks, having a pair of downsamplers and upsamplers with some filters. And I've found a good explanation from the MathWorks. You see, MathWorks, the company that produces MATLAB, MathWorks home site, where there is a good example about these two-channel filter banks. Anyway, so, and also I will briefly talk about the big picture of section 4.8, then move to the today's topic, quantization and encoding. And there are a lot to talk about. I hope I can cover everything I prepared. And then we are going to move to chapter 8, the DFT. So I have written down some equations already. So let's see. So last time we've seen some strange equivalent relation where we had two discrete time signals, the same discrete time signal pairs. Got it? So this two block system is same as this two block system. That was the claim. And here we have downsampler followed by a filter. And you may say that, oh, something's wrong. Well, usually when we talked about downsampler, actually filter preceded the downsampler. So we had a filter, usually anti-aliasing filter, and then downsampler. But here, be careful. To use this equivalence, you need to identify a downsampler and then a following filter. Got it? So this is significantly different from what we already know as now a common sense. Got it? Now, even though the convention is to use the Z transform of the filter, we know that under certain conditions, it's okay to use the frequency response of the filter, right? So here I have derived the truthness of these two different realization by using the discrete time Fourier transform of the output. Got it? So I will show you that the DTFT here in the A section and DTFT of Y in the B section are the same. Got it? So here, let me repeat. Unlike the usual decimator that has an anti-aliasing or some filter, followed by a downsampler. We have a downsampler followed by an LTI filter. Be careful. Now, we swap these two, apparently, but here we have a little strange thing. And as I just told you, here we may say this, ready? Because your Z transform and your DTFT are in the same form, except that you replace Z with e to the j omega, then you get DTFT. Got it? So for convenience, let me use DTFT to justify their equivalence. Got it? So in the left-hand side, the first thing is this downsampler. And I asked you to remember this one because this downsampler is similar to the uniform sampler that converts continuous time signal to a discrete time signal. So first, in the frequency domain, what you have is what? So here, this part and then that part is analyzed. So this downsampler part has output x sub a of m. I used a different index. Now, you can easily see that this guy has what? First, in the frequency domain, the sampling rate or downsampling factor. 1 over downsampling factor, right? And then you have what? Copy and paste of this spectrum, right? And not only copy and paste, you need to make it periodic. So here goes omega minus 2 pi L here, right? And also, when you convert, what happens? You have to divide omega by m. So this is the key here in deriving capital X sub a of e to the j omega. And then following filter is very simple. You just multiply DTFT of h, right? So here, this y of m has DTFT given this way. It should be clear. Otherwise, you have a big trouble for your second quiz. Now, let's see the right-hand side. First, you have what? You have DTFT of input multiplied by DTFT of this filter. And then you have downsampler. So at here, anyway, you have 1 over capital M sigma and spectrum, so-called spectrum folding, that is copy and paste, right? And that copy and pasted one will be what? The multiplication of capital X of e to the j omega and h of e to the j omega m. So here, as you see, this xb is what? xb is this one evaluated at here. Is it clear? It seems that it's not clear. I'm sorry. So let me see this one. So now let's see only this part. So let's ignore this one. So you have x sub b that is downsampled. And as I told you, after downsampling, the DTFT becomes what? The sampling rate times sigma and folding, right? So sampling rate times sigma and is folding. And when you fold, you have to make the period an integer multiple of 2 pi. And you have to scale by multiplying 1 over m. So same thing happens here and there just to get there. And now what is this one? xb of n has DTFT, this one, right? I just used omega tilde for convenience. And here, as you see that, xb of e to the j omega tilde with omega tilde replaced by omega minus 2 pi L divided by m. So if you plug in here and there, the first factor is the same as the factor here. And second one is a little bit different. Even though your m's cancel, you have omega minus 2 pi L. But good thing is that any DTFT is periodic with period 2 pi. So you can ignore this minus 2 pi L. So you have e to the j omega, which makes you the same result. Got it? So this is one way to show that this serially connected downsampler and filter can be swapped some way as a different filter. Actually, this filter is not the same as that filter, as you already know, right? Got it? Be careful. Here, this filter is different from that filter because let's say this one is H1. Then H1 of e to the j omega is here. Let's say this is H2. Then this is H2 of e to the j omega. Got it? So H1 has this one, but H2 has that one. Got it? So as you see, the exponent is different. So the function is different. Be careful. But anyway, so this is multistage decimation part. And we have almost the same thing in the interpolation part. That involves what? Up P, right? Upsampler. So here you have upsampler, but be careful. What we are focusing is this pair. So remember that in the upsampling, usually what do? We upsample, so we insert zeros first, and then we put an interpolation filter. So usually, what is the pair? Upsampler and filter. But here again, it's different. We have a filter and upsampler, and this serially connected, concatenated two systems will be replaced. Got it? So the scenario is almost the same. Now, let's see what happens. So similarly, let me just say this signal is that one, okay? And this signal is that one. Got it? Now, again, we derive the DTFT of this one and show that when we swap and replace the exponent 1 to L sub 2, by the way, upsampling factor is L2, is the same. So let's see. So when we handle upsampling, it's much easier to handle because of what? Because of this relation. And I ask you to remember this one, okay? So in upsampling, no sample is lost. Just zeros are inserted. So we have all the samples of the input here, XD, all the samples of XD, but we have capital L minus 1 zeros. Now, this signal is what? Sorry about that. Sorry. What am I doing? I'm sorry. Not this. Ugh. Yeah. Okay, so this entire thing is in this parenthesis. Got it? I'm sorry. So this thing is multiplied by e to the j omega L because I used L as the summation parameter. Now, under certain conditions, we can change the order of infinite sums. As I emphasized in math department, if you do this, probably your professor or your friend or TA will say, oh, stop, prove that one. But we know in electrical engineering, infinity means different something. So we just, with comfort, just swap the order. And then this XD comes here because it's not related to L. And here goes delta times e to the j omega L, where L runs from negative infinity to positive infinity. So you change L from some value to positive infinity. And when L equals KL, you have non-zero term. So this summation, infinite sum, actually becomes a single scalar. What is that? This one. Because L equals K capital L survives. So L equals K capital L. Now let's see what is this one. This is simply the DTFT of XD evaluated at omega equals omega capital L 2. Let me change. There's 2's. Got it? Now, so this is kind of upper half side, right half down, up, down. Okay. Anyway, let's see this one. Okay. No, not here. Yeah. So, not yet. So here, what is XD? XD is the signal here. And this signal is simply convolution of X and H1. So its frequency response is simply the multiplication of X, DTFT of X and DTFT of H1. Now you put what? Here, omega equals omega L2. Then what happens? You have the same thing as this one. Why, by the way? Why? Why do you have this one? If you upsample X, then what do you get here? If you upsample. And upsample signal is multiplied by this one. See that? Here, upsampling of that one will give you what? Just the signal input scaled by L2, right? So if this signal is upsampled, this one will be x of e to the j omega L2. Now, this should be multiplied to have the same thing. That's why you have H1 evaluated at z to the L2. Got it? So we have proved the equivalence. Then what happens? We switch these two. So you have upsampling, which inserts zeros, and upsampling, which inserts L2 minus 1 zeros. And then you have what? The filter. Of course, a little bit different by scaling in the Z domain. And then you have the same copy. Got it? So this is the story. Now, let's a little bit talk about two-channel filter banks. And you will see in advanced DSP, something called subband coding. And this may sound strange, but here goes a simple example. I'm not saying that this is the only way to use two-channel or multi-channel filter banks, but this is a representative example. Got it? And this example is much used in speech signal processing. for recognition and synthesizing. So if you have interest in this topic for your voluntary project, read some articles from the web and also search for Wikipedia and YouTube and other materials. Anyway, here was a simple example. So suppose you have a signal X and you have output Y. One of the methods in speech signal processing is to filter the input signal with a low-pass filter and do some processing and pass through high-pass filter and do some processing. Usually, low-pass components contain information about vowels, 모음들 we utter, and high-frequency parts contains consonant, 자음 information. So it's kind of good choice to have two filters. Of course, you may have multiple filters. And what we usually do is that we have a low-pass filter and high-pass filter. And in the frequency domain, what do we have here? Of course, the DTFT is periodic, but we may say this region close to plus minus pi is high frequency part. So this signal after low pass filtering will reside around here only. Similarly, you will have the output of this signal, output at that part will look like this. Now, you find a lot of space there, right? Which means you may reduce the sampling rate by downsampling. So here goes downsampling. Then what happens when you downsample? You rescale pi over 2 as pi, and you copy to make the entire signal periodic, right? So now you can process, here in this case, exactly you reconstruct, but sometimes here you process low frequency part with lower rate, high frequency part with low rate, right? And then you do something, right? Sometimes you may remove the noise in the low frequency part. For example, usually when we record using our microphone, what happens? There are DC interference like 60 hertz and their harmonics, right? You may have heard from some speakers, loud speakers, like when the switch is turned on, you heard some very loud woo type sound, right? That is usually 60 hertz DC power interference or its harmonics. And you may want to remove here. And also here, you may want to remove some hissing sound. As I told you, when we had tape recorders to record our voice and sound, the problem was that there was a lot of hissing sound, high frequency, white noise type thing. And as I once told you, when I was at your age, when I purchased some Korean companies, so-called similar to Walkman of Sony, and I couldn't hear the sound because of this high hissing noise, type background noise. And that one actually can be removed by some signal processing. Something like that. Got it? So here, apparently y of n is to perfectly reconstruct x of n. That is an example, simple example. Sometimes we do some signal processing this way. And of course, we may have more filters by dividing our entire input signal frequency range into, for example, 3 bands, 4 bands, 5 bands, 6 bands. No problem. If we divide into 6 bands, probably this downsampling factor would be 6. By the way, some people love this number and down arrow, number and up arrow. Even though in our textbook, we always put up-down arrow first, they read it 2 times downsampling. So to them, this is clear. 2 times upsampling. That's what they say. They are not saying that downsampling by a factor of 2. So there are 2 groups of people. So don't be confused. Anyway, so this is the key block diagram of section 4.8, digital processing of analog signals. So even though apparently there are 4 blocks, usually we have a single component that is sold by manufacturers. There are many famous A to D converter manufacturers. There are some Japanese companies like Anritsu, and I've read some specification of their product, and also Analog Devices, Texas Instruments. These 2 companies, probably if you have interest in investing in the semiconductor companies in the US, probably you've heard about SOXL and SOX related to the ETF 3 times, leverage and inverse ETF containing NVIDIA and other companies. And Texas Instrument and Analog Devices are a member of that ETF. They are very famous and dominating in the market. And usually they have something like this. Probably I've drawn this block diagram there. So it's not like a square, okay? They use some symbol like this. And here is the input and there is output. And if input part is a kind of little bit triangular thing, or you may say that, okay, it looks like a baseball home plate, okay? Anyway, so this part, this means analog. That means digital, got it? So sometimes you may have flipped version, but it's okay. This part is analog. Analog in and digital out. And A to D converter. And this A to D converter has anti-aliasing filter and C to D converter and even the internal downsampler. But they say that, they don't say that, hey, we actually upsample and filter and downsample. They don't say that. They just say that, okay, here is our product and the dip switches. If you put, for example, 5 volt, 0 volt, 5 volt, then you select some sync-like anti-aliasing filter, or if you select 550, then you have the zero the hold type thing, blah, blah, blah. And if you have 5 volt, 5 volt, 5 volt, and the maximum sampling rate, and 0, 0, 0, lowest sampling rate, blah, blah, blah. Got it? Okay. Anyway, so this is the way. Yeah, I've drawn this one. And also, this is digital out, means that actually this is already kind of line-coded binary signal. So we have this more, okay? So inside ADC, there are many things. Anti-aliasing filter, continuous to discrete time, some converter, and possibly filter, downsampler, and quantizer, and encoder, binary encoder, line, usually binary line coder. Anyway, something like this. And once I told you, not once, twice or 3 times, this part is not the major topic of undergraduate course, but our textbook has some exposure to the readers. So let me do it, okay? At least you'd better know where you can find the materials I didn't cover, because you may need this. So let's see. First, so after C to D conversion, What does that mean? You have a continuous time signal in our mathematical model, and you have a discrete time signal, which is actually sequence. And each sequence has, if it is a real valued sequence, each term is real value. And any real value requires infinite bits to describe, right? So we can't handle that in our electrical system. So we want to assign a finite number of bits, like 16 bits, something like that, for example, 8 bits. Then one way, I'm not saying that this is the only way, but one way is just what? Convert each term of the discrete time sequence to a vector of bits, 16, length 16 vectors, got it? And to do that, what people usually think is to what? As I drawn last time, one, two, three, four, five, six, 7, 8, something like this. So this is the input, and that is output. So first, since you, for example, in this example, we are going to assign 3 bits. We may have maximum 8 levels. So here we have 8 levels, 1, 2, 3, 4, 5, 6, 7. And if we have this method to quantize, then what happens? If the signal goes over this range, they are all the same as that value. If signal level, this is the input, goes down, that all the values are assigned here. And most of the textbook says this way, but actually it is not true. Okay? There are many other methods. The first thing is that, what about the spacing between these output? First, they could be the same. Second, they could be different. And when they are the same, usually it's called uniform quantizer. Which means non-uniform quantization is possible. And you may wonder when we need that. Actually, if you have seen some introductory digital communications textbook for undergraduates, there is mu-law, m-law, something like that to convert our digitized speech signal to number of finite, some finite length bits. And people have drawn some histogram of our sampled voice signal, and they have found that in the low amplitude part, we'd better assign more bits, something like that. Got it? But anyway, so this is the first thing. And second one is that some implementation of quantizers are not this way. What does that mean? This is actually so-called clipping quantizer. So if it goes over some range, then the output is saturated. But it's not always true. Some have very interesting thing. It's repeating here. Up to some points. Not infinity, but. Got it? Some quantizer has strange thing. If the input value goes over some range, it's 0. So depending on how you build your A to D quantizer, your mapping curve may differ a lot. Okay? So you have to have an open mind. What you have seen in the textbook is an example, just to show you what can be done just for the undergraduate students. There are many different ways, and you may wonder, what's the use of this one? But I'm not a circuit guy, but what I heard is that some method very efficiently quantize the signal has this repeating pattern. Some technology, I don't know exactly, some way of building quantizer gives you this saturation thing. Got it? Some method gives you this null type response. Got it? So, and also, of course, in every cases, we may have uniform spacing or non-uniform spacing between the quantization level. Got it? So here, we assume the first one, so saturation or clipping type quantizer. So let's see. So here in this region, you have this entire curve is mapped to 3 delta. And here, as you see that the spacing is uniform, right? And here, this is mapped to 0, 1, 1. Got it? After binary encoding. Something like this. So this is actually sample and hold type thing. So actually, this sample is mapped. This sample is mapped. This sample is mapped. Something like this. Got it? So as you see, there could be some error when you quantize. This is significant in some times, but if you have very small value of capital delta, then your error would be very small, at least. And this error is not a linear system output. So you can't do something like this. Okay, here is quantization system. And here goes my signal x, and here goes my capital Q of x. And this one is a non-linear function. Of course, memoryless. So it cannot be implemented using a linear function. What does that mean? We are doomed. It's very difficult to analyze. But people have tried to find out. So here goes some strange method. They wanted to rewrite the output as the input plus so-called quantization error or noise. And you know that this error is a function of input and this mapping rule. Got it? So it's not easy to analyze the output, but people heuristically have found something. What? If you have enough number of bits, which means that if you have enough very small quantization level, then you may, not always, you may approximately say that quantization noise is independent of the input. That's absurd. And it's a white noise. And in order to justify that one, people have research. See that? This is a clipping type thing. And you see this quantization of xn, now the sequence, is modeled as an input signal plus quantization noise sequence. And here is a plus. So sometimes we may call, as you see here, the quantization noise or error is called additive. But be careful. In digital communications, when you have additive noise or additive interference, it does not only mean you write the noise added to the signal. We usually imply it's independent of the input, even though the additive just means additive. So be careful. Got it? So even though it says additive, actually it's additive but dependent on the input and this quantization mapping rule. But as I told you, people wanted to have something similar to that one. So they have considered clipping type quantizer, and there are too many possible inputs. So why don't we just consider simplest one, sinusoidal signal? So sinusoidal signal, that is the input to the quantizer, quantized by the uniform quantizer with saturation. And you see that if the value goes over some limit, then it is clipped. Now, you numerically, using MATLAB, for example, subtract these two to have error sequence. For example, in this case, actually, the signal is sinusoidal signal, and this is the quantizer output, and this is the error signal. So if you add these two signals, then you have a beautiful sinusoidal signal. Can you see that? And if you take a look at this one, it looks like a white noise, but it is bounded. Why? Because of the nature of our quantizer. Our quantizer gives that value if our input is only in this range. So error cannot be bigger than some value. So in that sense, it's not a kind of white Gaussian noise or something. But in many cases, people even bother the quantization noise as an additive white Gaussian noise. That's absurd, but they do that. Now, in order to justify their independent additive thing, actually showing independence is impossible because it's not independent. But what they wanted to do is that, hey, anyway, we usually implement second order based signal processes. And of course, you don't know what do I mean, but when we handle random processes, if we want to have a linear system, then we usually only utilize the second order statistics, which means mean and autocorrelation, variance, that thing, not kurtosis or something of higher order moments, not that, up to second order. So up to second order, what could be a good description? Of course, in the time domain, first, what? Histogram of each sample, which corresponds to the first order PDF of the random process. And then you may consider second order PDF, and that's too complicated. So what do? They calculate autocorrelation function over random process. And after you compute the autocorrelation function, then of course the next method would be Fourier transform the autocorrelation function, which will give you a power spectral density. Of course, this part is just ignored by me, unfortunately, in this undergraduate DSP. So that is why some professors in our communications and signal processing subgroup of post-DAC E department now talks about, hey, what do we do with the graduate level DSP, where we want to talk a lot about processing of random processes, digital signal process of random process. But anyway, so here goes the hopefully correct probability density function of the error signal. So it's bounded, right? As I told you, it cannot be more than half of the delta and half of the negative delta. And we want uniform distribution. Unfortunately, well, here, B plus 1 is the number of bits. I don't know why plus 1, but anyway, B plus 1 is the number of 16 bits, 8 bits. You see, interestingly, the histogram looks more flat when you have enough number of bits, large number of bits, which matches to the claim, right? Hey, good. So 16 bits, 8 bits, well, now, so this is related to the first order PDF. To talk about the second order thing, we have drawn the power spectral densities of the error random process, actually, error signal. Here, B plus 1 is 4, B equals 3, 7, 11, 15. So in this direction, your number of bits increase. And fortunately, the power spectrum becomes flat. So this kind of justifies their heuristic modeling of quantization noise. So they say that, okay, see that? I don't know the exact probability distribution, but if we focus on the first and second order moments, we are happy. Let's just assume that it's not Gaussian, but it's uniform white noise. Got it? And this is related to the SQNR. And I'm not going to talk much about it, but please remember this one. This is signal to quantization noise ratio. Usually in communications, we have the acronym SNR appearing everywhere. But when we have quantizer, especially this kind of scalar uniform quantizer, we talk a lot about SQNR. So just remember this one. And if you confront this terminology in your research or in your development in your future career, then, okay, I remember this is signal to quantization noise ratio and blah, blah, blah. By the way, this signal to quantization noise ratio may differ a lot if you change the input signal. So usually, these nonlinear, to analyze nonlinear behavior of the uniform scalar quantizer, they restrict their input to sinusoidal signals, or a very simple thing. Otherwise, analysis is impossible. Our handout does not talk about some formula, but there is a very famous and simple formula about the SQNR. So SQNR equals some almost 6 dB times some, negative 6 dB times the number of bits, blah, 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 something like that. And if you see that one, remember this one. That is not for every possible input signal to a quantizer. That is for sinusoidal input, blah, blah, blah. Got it? Anyway, so up to here, you have A to D converter. Now you have D to A converter. And as I told you, if this is in and this is D to A, this part should be square, and that part could be a part of triangular, which means digital in, analog out. And if you see that in the schematic diagram, then it means some product. That means not only the input signal is a bit stream, possibly line coded, or sometimes vector, but anyway, the output is really an analog signal, continuous time. Got it? But as I told you, this real world product called the D to A converter is mathematically abstractized. As I told you, we use math models. So in our mathematical model, as you've seen already, we have some strange block like this. Conversion from DT signal to continuous time impulse train, modulated impulse train. You know what is this, right? And this xs of t is sigma xn continuous time delta function and nt. So you have this strange signal that does not exist in the real world, just for mathematical convenience. And then here goes our interpolation or reconstruction filter. And here is our reconstructed signal, which could be the same or different from, a lot different or a little bit different from our original continuous time signal or desired signal. Be careful, as I told you, even though our textbook says sampling period, capital T, and sampling rate 1 over capital T, most of the specifications from our industry, so if you see Japanese companies, ADC, DAC spec, or Texas Instruments or analog devices, DAC specs, they usually talk about conversion rate, got it? When they have D to A converter, got it? So conversion rate is 1 over capital T. In the ideal case, we have ideal low-pass filter, but that's not necessary. Practical D to A conversion, usually this binary signal is already kind of abstractized to a discrete time sequence. But usually in their circuit, they have some scaling mechanism first, because they do not want to have some signal that is too large or too small. So usually they have some amplifier that can be disabled by our choice. So usually D2A converters has a lot of pins, and we may select to disable or enable some function. And one of the function is kind of automatic gain controller. You will be confronting in the communication systems. But I'm not going to talk too much about that. And long ago, this textbook is very old. Long ago, usually the D2A converters has so-called zero order hold, which means that our interpolation filter has impulse response, time domain, rectangular pulse. So our reconstructed signal has spectrum that has sync square times something. But we don't want that. So this should be compensated by filter outside DAC long ago. But now that is also combined in the product. So don't worry too much about it. But anyway, so here goes the problem as I mentioned already, that appeared in one of the midterm and exams and final exam of 1995 spring semester when I was a student taking the introduction to DSP. So I had to justify why our compensating filter must have this magnitude response in the exam. Ready? And now you know, right? If we have zero order hold here, then we need to invert the spectrum of zero order hold. Otherwise, we don't have a flat ideal filter. Ready? So, okay, we are almost there. So our textbook says, here is a D2A converter and compensating reconstruction filter. But as I told you, you don't need that. Usually now, you can even select by choosing some input pins. You may choose some square raised cosine interpolation filter with some different roll-offs. Now you can do that. Okay. Okay, so we are done. And you may say, hey, this is section 4.8 or 9. What about other sections? As I told you, I will skip that because these sections are related with random processes, and which I'm not going to cover, fortunately to you. By the way, I found that other universities, kind of our competitors, they also have the senior level introduction to digital communications and other similar level introduction to digital communications or something. And I have found that the universities require a lot of things from students. And it seems I felt guilty that I'm not pushing you too hard for you to develop yourself through this course. But not this time, okay? Probably next year, I will put tons of MATLAB homeworks so that almost everyone wants to drop the course. Okay. Okay, here goes chapter 8. The topic is, as I announced, DFT. The first thing you have to remember is this one, because it was a real pity. Some students, after they graduate from Department of Electrical Engineering, they can't distinguish these two. You never do that, right? DTFT and DFT are related but different. So let me show you first. DTFT is something like this. So you have input discrete time signal, and you have output a function of omega, real number. So this is DTFT. So DTFT is a transformation of a sequence to a function, periodic function. What about DFT? In DFT, you have a vector of finite length, usually real or complex length n. And here goes your output that has the same length. Right? So they are different, right? It's like you have two systems. One is accepting only sequence, the other is accepting only vector. How can they be the same? Of course, in some conditions, they may be closely related, but they are totally different thing. Okay? So please, please, please remember, DFT is not DTFT. Second one is this one, FFT. FFT is fast Fourier transform. But this is also a misnomer. As I told you, misnomer is 잘못된 이름, 오류 명명. Why? Because this is actually fast algorithm for DFT. But they just because we always want to be economical, so we have FFT here. So FFT is an algorithm to computationally efficiently implement DFT for some cases. Here, for some is related to the value of this input vector and output vector. Usually, not always, n is a power of 2 to the power of some value. Then people say that we have efficient algorithm to implement DFT. Of course, it has inverse transform called IDFT and IFFT. Ready? And currently, the most important the wireless digital communication standards like Wi-Fi and our 5G, 4G systems for land mobile telecommunications, they all employ so-called OFDM waveform. Here, orthogonal frequency division multiplexing, where your cell phones or wireless access points have what? These algorithms inside to perform DFT and IDFT many, many, many times within a fraction of seconds. Got it? So in this way, in some sense, this is the time for DFT. When I was at your age, it was not. So this is the introduction. And okay, here is the big picture of this course. And there are many chapters. And we are kind of skipping this part or deferring this one and more focusing on here. You see, 2, 3, 4, and now 8. Got it? DFT, and then probably FFT. So, yeah, I already mentioned. And here goes the DTFT review. So, even though you have single equality, but this is for what? Actually, you have uncountably infinite scalar equals scalar, right? Because you find a function. And here is a DT signal. And here is a function, as I told you. And what is the meaning of this one, by the way? What is the meaning? There are many ways to interpret this one, but whenever you have summation of some A sub n and B sub n, it's approximately A, B inner producted, or if you want, something like this for real valued vectors, and something like that for complex valued vectors. So let's view this one as a product of two things, x and e to the j omega n with conjugation. Okay, so here, this one may be interpreted as something. So in that way, you have something, some strange notation, but anyway, something like this. So it's an inner product. And what's the use of inner product? Of course, inner product is simply an inner product. You just multiply these two. Geometrically, what does that mean? Actually, when we were high schoolers, we learned inner product of two vectors when we wanted to extract the magnitude of some vector toward some other direction. You remember that? So it's like, okay, here are two vectors A and B, and inner product is related to this length, something like that, right? Especially when you have the vector B has its norm 1, something like that. So this is related to A inner product by B divided by the norm of B, something like that. Got it? So this inner product is kind of try to find the component along that direction. So what does this mean now? This inner product is to find out the magnitude of the component in X that is related to a specific omega. So you have complex sinusoidal signal, and you wanted to extract the component of that complex sinusoidal signal with specific omega. Got it? And if you change the value of omega, then you find different frequency component of the signal. So this is one way to interpret DTFT. Got it? And actually, it's not a lie. That is exactly the idea of DFT. In DFT, you handle finite length vector, and you really project the input signal to a specific direction. And that's what you are going to see. Got it? So they are not unrelated. However, they are different. Let me repeat. They are different operations. However, they are closely related. Okay, this is too much. Yeah, here goes some strange, and really I hate this notation. I will not talk about this today because it's too confusing. Okay. So since we have around 10 minutes, I will give you a big picture of this chapter 8. So here goes the title of section 8.1. And here you have periodic sequence, means that you have DT signal that is periodic. Got it? Whenever you have a periodic signal, some of your neurons says that Fourier series, Fourier series, Fourier series, right? So you have Fourier series, DT Fourier series representation of this signal. So here goes K, N, strange notation. You have CK, AK, let me use CK, e to the J, 2 pi divided by N, K, N, something like that. Where CK is called the Fourier series coefficient, and you have the way to compute that one, something like that. That's what you learned in signal gen systems about DT periodic signal and DT Fourier series. Got it? So if I am the author, I will put like this. So DTFS. Got it? Otherwise, it's too confusing. Okay. And amazingly, here goes big exclamation mark, 느낌표, exclamation mark. This Fourier series coefficient, DT Fourier series coefficients, can be obtained by DFTing a single period. Got it? I'm not saying that the output is the same because of the scaling issue. And you've seen this one actually where? Your midterm exam or first quiz. That's what I remember. Okay. Even though you didn't relate the result. Okay. So section 8.1 will say this. Suppose you have a discrete time periodic signal. Now you take a single period to form a vector. Now it's a finite length vector of length n. Now you perform so-called n-point DFT. Here n means that your DFT may accept different lengths of vectors. So actually 2-point DFT is different from 3-point DFT. So we prefer to specify what is the length of the input and output. Okay? So you transform that vector of length n using n DFT. Then you will have length n vector output, right? That is related to the Fourier series coefficients. So in this way, DFT is a very efficient way to do the discrete time Fourier series representation. Yeah, this is done. And jumped. And this is another one. So you have a signal, DT signal, then you have DTFT, right? Now, how many pairs of omega and x do you have? Because it's a function. DTFT is a function of real value omega, right? How many pairs of omega and function value do we have? Uncountably infinite, even though we only need to find for omega in the finite interval from 0 to 2 pi or negative pi to pi, but still uncountably infinite. If we want to plot using MATLAB, anyway, we need to kind of evaluate the function uniformly in the omega domain. So we somehow consider evaluating the DTFT over a discrete time signal as some omega 0 times k with some specific omega 0 and k for some integer. But as you know that not all integer, because if you choose omega 0 as a rational multiple of 2 pi, actually, if you evaluate at z, the integer, it becomes a periodic signal, right? So you don't need to evaluate for all k, but anyway. So in that case, how many samples do you have? Finite, right? So if omega 0 is some 2 pi p over q, something like this, right? Now, let me ask you, is it easy to compute the DTFT of a discrete time signal? Of course, no, right? Because this is defined as what? Infinite sum evaluated for infinite different choices of omega, right? So this is infinite, and that is infinite. That's why DTFT is not best fit with digital computers. However, in the digital computers may choose some very small omega 0 positive and have some kind of sampling of this DTFT, evaluating uniformly. In that case, finite number of samples would be okay. For example, let's say this is the original DTFT of some signal. Now, what you do is that you choose some small interval, which is the rational multiple of 2 pi, and then you evaluate, and you have repeating values, right? So now the question is, how can you obtain these values? Using DFT. And if you are very alert, then this question is a nonsense. Why? Because anyway, we need to compute this one to have omega 0, right? Still, we have a big problem. I have a big problem, right? You need the entire signal. What can you do? How can you handle the DT signal, mathematically modeled DT signal, using our finite memory computer? Truncation, right? So maybe you just want to replace this by some m, right? So you have 2m plus 1. Saying that, okay, from negative m to positive m, almost the important signal component in X is contained, right? You may say that. Then let me ask you. So this is now an approximated version of the signal, right? After truncation. Now, question. Can we compute that one now, right? Now, this one is what? Discrete. You have finite number of values. Can you compute that using DFT? That is the question. And of course, the answer is yes. That's why we learn DFT. Okay? Okay, here goes another section. Yeah, this is more appealing. So just we've truncated the signal, but suppose the signal X is time limited, means from some N1 to N2, it has non-zero values, and all the others, it has 0 values. Great, right? Now, let me ask you a question. Can you compute the DTFT, of course, evaluated at some omega 0 k, using DFT of some part of this one? And you may say that, hey, just cut here to there and to do the DFT. Actually, that may have a big problem. Why? Because the length may be something like 4,532. Why do I say this? Because sometimes we have a very large signal, of course, but we now have very large memory, but general DFT still requires a lot of computation. So we want to choose some n, that is 2 to the n DFT. So probably what you want to do is that, okay, 1024 times what? 4. Okay, let me use 4096 point DFT, which can be efficiently implemented using fast algorithm. Now, let me ask you, from where to where are you going to cut? And you may say that anywhere, right? As far as these non-zeros are contained. But their outputs are different because you put possibly zeros for some computation more, and sometimes you push zeros to the bottom of the input vector. And of course, they generate different outputs. And how can you change that values to have this one? And you may say that, okay, Professor Joe is just not prepared for the chapter 8 and just takes the time. No, actually, this is the key, okay? Students make a lot of troubles when they have that question. And you are, you are going to do your homework exactly the problems I told you. Ready? Where to where when you cut, and how to adjust your FFT output to have exact DTFT coefficient, and how they are related, something like that. Got it? Okay, I remember we have one more. This is properties of DFT, not that one. Yeah, this is also very important. In discrete time signal processing, of course, this is one of the most important issues. And convolution is very computationally intensive. Now, we know that X and H are time limited, and we may choose some 2 to the power of something to lengths to contain both of the signal lengths. So, for example, this is X of n, and that is H of n. Got it? And this is, you choose here, you choose there, and they are, for example, contained in length 1024. So you may use 1024 point FFT. Now, can you compute convolution using DFT? Currently, you may say, what? But actually, you can do that under certain conditions. So DFT is very, 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 very versatile. 여기저기 쓸 수 있는. Got it? So I believe that's all. Yeah. And then all the details of these things. Got it? So expect a lot. Here comes the core of this course. Okay, that's all for the day.